while the entire world is still chasing lithium batteries as if they were the only possible solution, a new, quiet revolution is gaining momentum and promises to turn everything upside down. What once seemed like a mere technical curiosity in laboratories could now become the trigger for a historic shift in the automotive sector. We're talking about sodium-ion batteries. Yes, sodium, the same element found in table salt. But don't be fooled by their simplicity. This alternative could be up to 100 times safer, cost a third of the current price, and charge twice as fast. And the most shocking thing? Prototypes already exist that promise almost 5 million kilometers of useful life. Lithium's biggest problem isn't just price. It's the explosive combination of scarcity, environmental impact, and fire risk. In recent years, global demand for electric vehicles has skyrocketed, and with it has come a race for lithium. Countries like China, the United States, and Australia are competing for this resource as if it were the oil of the future. But there's a troubling detail to this story. Lithium is becoming too expensive, difficult to extract, and, in many cases, concentrated in politically unstable areas. For an industry seeking to popularize electric cars, this dependence has become a real threat. And that's where sodium comes in. Abundantly found in the Earth's crust and much easier to obtain, sodium can be extracted without the same brutal environmental impact caused by lithium mines. This changes everything. Using sodium as a battery base opens up a range of mass production possibilities without the bottlenecks and geopolitical conflicts that hinder lithium. Furthermore, costs plummet, making it possible to imagine affordable electric vehicles even for emerging markets. Something that, let's face it, still seems distant with the current prices of Tesla and its competitors. Now imagine Tesla putting this into practice. It wouldn't be necessary to abandon lithium altogether, but to integrate sodium batteries as an alternative for simpler, cheaper models. This shift could pave the way for the long-promised Tesla at $25,000 or even less. And the market is already starting to react. Chinese giant CATL, Tesla's main battery supplier, is not only investing heavily in this technology, but has already begun small-scale production. The goal? To reduce the cost to less than $40 per kilowatt-hour. If that happens, it would be like dropping a bomb on the heart of the current lithium-based production chain. Besides cost, recharge time is another area where sodium is surprising. In recent tests, prototypes managed to charge up to 80% in just 10 minutes. For anyone driving an electric car, this is almost magical. Imagine leaving home late, stopping at a gas station, grabbing a quick coffee, and returning with the car practically full. It's a huge leap compared to the roughly 30 minutes required for current batteries. And best of all, this technology is more stable, less prone to overheating, and won't explode under pressure. This means a car with a sodium battery can be safer in accidents and even eliminate the need for certain expensive protection systems. And as if all this weren't enough, the lifespan of these batteries is another slap in the face to the competition. Advanced models have been shown to last up to 10,000 charging cycles, which equates to about 20 years of continuous use. This is more than double the durability of the most durable lithium-ion batteries available today. With this durability, consumers don't need to worry about replacing the battery during the car's lifespan. The impact on resale value, consumer confidence, and overall market perception can be enormous. After all, who wouldn't buy an electric car knowing the battery will last 2 decades? Interestingly, until recently, these ideas sounded like science fiction. Even among engineers, talk of sodium batteries lasting millions of kilometers and recharging in minutes seemed far-fetched. But technological advancements have overtaken this skepticism. Universities and companies around the world have been accumulating patents and laboratory tests with increasingly promising results. The turning point came when the materials used in the electrodes began to be redesigned at the atomic level, allowing for greater ion density and greater stability. This opened the door to real applications, rather than just conceptual prototypes. Of course, adopting a new technology on a large scale isn't as simple as flipping a switch. There are technical challenges, logistical adjustments, and an entire supply chain that needs to adapt. But the fact is that major automakers are already watching. And whoever gets ahead can dominate a billion-dollar market before the others even start racing. Tesla, with its obsession with innovation and vertical control of production, seems to be the company best prepared to make this leap. It hasn't announced anything officially yet, but behind-the-scenes rumors and CATL's investments indicate that something big is brewing. Despite sharing electrochemical principles with lithium batteries, sodium-ion batteries have a unique internal structure. Instead of using expensive and scarce metals like nickel and cobalt, they rely on widely available elements like iron and manganese for the cathode. For the anode, the most common material is hard carbon, known for its high stability and ability to withstand repeated charge cycles without significant degradation. These components not only reduce the final cost, but also make the manufacturing process less dependent on specific regions of the planet, avoiding the market concentration faced by lithium. The way it works is almost a reflection of what we already know about lithium. During charging, sodium ions migrate from the cathode to the anode through the electrolyte, a liquid solution that acts as a bridge between the two poles. When the car is used, the path reverses. The ions return to the cathode, releasing energy. This simplicity of the mechanism is one of the most striking points, because it means that current factories, designed for lithium batteries, could be adapted to sodium without a complete rebuild, saving billions in investment and accelerating the transition. The breakthrough in recent years was the realization that, even with an ion larger and heavier than lithium, sodium could achieve competitive performance. This was only possible thanks to advances in electrode materials with more porous structures, allowing ions to move more freely and quickly. This seemingly technical detail is what is bringing sodium's charging speeds closer to those of lithium, and, in some cases, even surpassing them. Today, there are prototypes that can go from 20% to 80% charge in less than 15 minutes, something unthinkable when this technology was still in its infancy. Another intriguing point is the ability to maintain performance even in extreme temperatures. While lithium loses efficiency and risks instability in extreme cold, sodium appears to handle adverse conditions better. This is due to its greater tolerance to temperature variations and the way ions interact with electrodes. In environments as low as 30°C, for example, some sodium cells can still retain over 90% capacity and charge consistently. For countries with harsh winters, this characteristic can be a determining factor in choosing between an electric car or a combustion model. In terms of safety, the difference is also striking. By nature, sodium is less reactive than lithium, meaning a lower risk of fire or explosion. Stress tests, such as direct puncture or exposure to fire, have shown that sodium cells withstand extreme conditions without immediate combustion. This resistance opens the door to lighter vehicle designs, as there's no need for such robust armor to prevent a potential catastrophic failure. In a market increasingly concerned about safety, this could be a decisive factor. Of course, not everything is an immediate advantage. One of the challenges remains energy density. Because sodium is heavier and takes up more space than lithium, it stores less energy per kilogram. In practice, this means that, to offer the same range, a sodium battery would need to be slightly larger or heavier. But this obstacle is shrinking. New material combinations, such as the so-called Prussian white in the anode, are helping to increase this density, bringing it closer to lithium levels and paving the way for applications in longer-range vehicles. The environmental impact is also worth highlighting. Without the need to extract rare and polluting metals like cobalt and nickel, the sodium battery's ecological footprint is much smaller. This not only attracts conscious consumers, but can also help manufacturers meet increasingly stringent environmental targets. For automakers like Tesla, which position themselves as leaders in sustainability, this is a strategic advantage that goes far beyond technical performance. The abundance of sodium compared to lithium is one of the most fascinating aspects of this new technological path. While lithium depends on specific geographic reserves and faces constant fluctuations in price per ton, sodium is present in virtually every corner of the Earth. It is estimated to represent about 2.6% of the Earth's crust, making it not only more accessible but also less susceptible to market manipulation. This opens a unique window of opportunity for manufacturers seeking geopolitical independence and supply chain stability, essential in a sector still suffering from the side effects of the pandemic and the trade war between major powers. This abundance is directly reflected in the cost. Simpler extraction, more common materials, and environmentally friendly processes make sodium an extremely competitive option. According to recent data, CATL can now manufacture sodium batteries for around $70 per kilowatt and aims to reduce this value to below $40. Just for comparison, the cheapest lithium batteries on the market still cost around $90, use $100 per kilowatt if this promise is fulfilled. The impact on the final price of electric cars will be immediate and profound. The equation is simple. With cheaper batteries, vehicle production costs fall. And when production costs fall, consumer prices can finally reach affordable levels. Experts like Tony Seba already project that, with this new generation of batteries, the most basic electric cars could reach the market by less than US $5,000 for an automaker like Tesla, which has been toying with the idea of launching an affordable model for years. This is the missing piece of the puzzle. The much-vaunted $25,000 Tesla may even be surpassed by something even cheaper, and that changes everything. Market logic is also changing. With more affordable cars, the mass adoption of electric vehicles is no longer a distant goal, but a tangible reality. Developing countries, previously left out of this electrification process, are now becoming strategic markets. Brazil, India, Indonesia, and several African countries could see an explosion in demand, provided costs actually fall as expected. And this global expansion also benefits Tesla itself, which gains scale, reduces fixed costs, and expands its influence at an even faster pace. Another strategic advantage is the versatility sodium offers for multiple applications. Unlike lithium, which is typically reserved for more expensive or long-range models, sodium can be used in compact urban vehicles, electric motorcycles, short-range delivery trucks, and even residential or industrial storage systems. This allows manufacturers to diversify their product lines, serving niches that were previously economically unviable. And because maintenance costs also tend to be lower, the consumer experience improves from start to finish. From a logistical standpoint, the shift to sodium also represents relief. Concerns about lithium shortages, which were already being treated as a potential global crisis by 2025, could be alleviated with the introduction of this new technology. Demand for lithium is expected to continue growing, but with sodium as a viable alternative, pressure on mines and prices will be reduced. It's as if the industry has gained a second lung to breathe, better balancing resource consumption and creating room for further innovation without the burden of imminent shortages. Tesla, as usual, has yet to make any public decisions about using sodium batteries in its vehicles, but the signs are everywhere. The partnership with CATL remains strong, and rumors about internal testing of new battery packs have been intensifying. If Elon Musk decides to embrace this technology, it would likely happen first in an entry-level model, possibly an urban hatchback aimed at markets like China and Latin America. This would allow the battery's performance to be validated in real-world situations without risking the reputation of its premium models. Safety, long a concern in electric vehicles, reaches a new level with sodium-ion batteries. Unlike lithium batteries, which can spontaneously combust under certain conditions, sodium batteries are inherently more stable. They don't react violently to heat, pressure, or punctures. This means that, in a serious accident, the likelihood of an explosion or fire is drastically reduced. Tests conducted by CATL have shown that these batteries withstand even extreme simulations such as multidirectional compression, nail punctures, and even direct fire, without combustion. This resilience comes not only from the sodium chemistry, but also from the materials used in the electrodes and the type of electrolyte employed. Because sodium is less reactive than lithium, the risk of internal short circuits or uncontrollable thermal reactions is much lower. For the end user, this translates into a more reliable car that's less susceptible to catastrophic problems, something that still tarnishes the image of EVs in some regions. In fact, this added safety may allow manufacturers to reduce thermal containment systems, which in turn makes the vehicle lighter and cheaper. Another impressive factor is how these batteries perform in extreme temperatures. While lithium batteries' performance plummets in cold weather, sodium batteries prove surprisingly robust. In laboratory tests conducted at 30 degrees Celsius, some cells maintained 93% of their capacity and managed to charge from 30% to 80% in just 30 minutes. This may sound technical, but in practice, it means you can start your electric car after a snowstorm with the same confidence as a gasoline-powered car. And this detail, as simple as it may seem, is crucial to a model's success in countries with harsh climates. Performance in extreme climates also reinforces the use of sodium batteries in other applications, such as city buses, delivery trucks, and even military vehicles. These sectors require reliable equipment in challenging conditions. And until now, lithium batteries have always imposed temperature and safety restrictions. With sodium, these limitations can be overcome, opening up a completely new horizon for the electric mobility industry. Tesla, which already operates with stationary storage solutions and light commercial vehicles, would have much to gain from this versatility. But perhaps the most surprising aspect of all is their durability. Most lithium batteries last between 2,000 and 3,000 charge cycles before showing significant degradation. State-of-the-art sodium batteries are reaching the 10,000 cycle mark. That's close to 20 years of continuous use, or about 4.8 million kilometers driven. For comparison, that's like traveling around the world more than 120 times on a single battery. For the consumer, this eliminates the main headache, the high cost of replacement after a few years. This longevity also has a direct impact on sustainability. Fewer battery replacements mean less electronic waste, less resource extraction, and less energy consumption to manufacture new units. And because sodium batteries use less toxic and more recyclable materials, the product's entire life cycle becomes much more environmentally friendly. This can be a key differentiator when it comes to meeting environmental targets and aligning with ESG guidelines being mandated in markets like Europe and the United States. Still on the topic of sustainability, it's important to highlight that these batteries eliminate the use of metals such as cobalt and nickel.